Hi guys, so I want to start with the example like this in your PowerPoint slides. It was right after we did one with a traffic light, and then we had one on the incline with the car, where we had to find time and then acceleration. So I want to do a couple more examples in terms of kind of free body diagrams, sum of forces, things like that. And then we're also going to look at an example of Atwood's machine today. Now, today as well, I left instructions, and remember that if we're in second bell, Taylor is in charge. If we're in fifth bell, Chris is in charge. So, Taylor or Chris, if you would find the apple on the desk, and if you would also find the pages that say Isaac Newton by James Gleick, then pass these papers out and let's kind of go over those really quick. So let's just pause the video for a second. Okay, guys, on your paper for Isaac Newton, I wanted you to read up until through chapter 6, and I wanted to talk about that this week. I thought that it may be more beneficial if, as all of our classes, so both of our classes combined, we kind of do this maybe together. So your assignment for Isaac Newton's first 6, we may even do 7 chapters, 6 or 7 chapters is going to be with a partner. You are to create a 3 to 4 minute video over one of the chapters explaining Newton's life or accomplishments from Gleick's book. This video should be a creative way to express Gleick's representation of Newton. So I actually am changing that assignment slightly, where it's not just going to be with a partner. I want you to get in a group of 3. So in second bell, there are 15 of you, so we should have 5 groups of 3. And then in fifth bell, there are 10 of us, so we could have 2 groups of 3 and 1 group of 4, or we could do 2 groups of 3 and then 2 groups of 2. So fifth bell, I'll let you decide that. The reason that I need you to, Taylor and Chris, to take this apple is because I'm going to place the chapter selections in the apple, and you'll draw for those. Each group is going to draw. And when you draw your slip, that's going to tell you what chapter in Newton's book you're doing, or what video, or what chapter you're going to be making your video on. When you have chosen in second bell your slip, just go ahead and throw that chapter away in the trash can. Don't put them back, because we'll do different chapters for each class, and then we'll just watch those videos. We'll watch those videos together in class on Monday the 25th or Tuesday the 26th of November. So this is what I'm going to be grading your video on. So let's just go along with these bullet points here. It says, I will be grading you on an accurate reflection of content in the assigned chapter. So that may include, content that Gleick talks about Newton in those specific chapters, but I also want maybe some inferences that you have drawn as a group about that chapter. Tell me maybe different connections to current events. Does this relate to something that's happening today? Any questions that you had as you were reading the chapter, you should pose those questions or try to answer those questions in your video as well. And next part is kind of this creative outlet in which you present the material. So I've heard some of you say the book is a little dry, so make it interesting, make it very creative. So you may want to make something, memorable, spark attention, maybe humorous, don't go too far, make sure we have a boundary, or just being thought-provoking. So those different things in terms of your creative outlet are what I'm looking for. Your length of your video is also what I'll be grading on. So it should be between 3 to 4 minutes. If it's under 3 minutes, I'll probably be way harsher than if it's a little over 4 minutes. video quality. So if you are taking a video, we shouldn't be going like this and then everybody's gonna just go crazy because they're trying to watch your video, but we can't really focus on it because we're shaking so much. So that's kind of what I mean by video quality. Just make sure that it's not really shaky, or maybe like transitions are pretty bad. And then the due date for this is going to be Monday, November 25th. And I want to make sure that I have that before class starts, because I'd like to watch them either Monday or Tuesday. So we will do that before we leave for Thanksgiving break. When you draw for your chapters, what I would like you to do is immediately today, like right now, post on the blog who is in which group, and then tell me what chapter those groups are going to do. So then that way I have an idea of who's in each group and then what chapter you're doing, so that way I just know. So due the 25th. You have all the things that I'll be grading you on, 3 to 4 minutes. If you have questions on this, just email me or post on the blog and I will email you right back. So, okay, there's that. Make sure you post on your blog right now and tell me what chapter you got and who's in each group. And then let's go ahead and get started on our examples here. Okay. So for this first example, we have two blocks of masses M1 and M2, where M1 would be greater in mass than M2. They are placed in contact with each other on a frictionless horizontal surface. A constant horizontal force will be applied to M1. Find the magnitude of the acceleration of the system. So before we even draw a free body diagram, I think we should draw a picture of the situation first. So I have two masses, and they're in contact, and they're on a flat horizontal surface. We're assuming that's frictionless. So here's M1, and here's M2, because M1 is greater in mass than M2. And it said that we have an applied force, some applied force, we'll just call that force applied, that's being applied to mass number 1. So that's what my overall system looks like. And I want to find the magnitude of the acceleration of the system. So I know if I look at the forces that are acting on mass number 1, because this force is being applied to mass number 1, which means if mass number 1 is going to move, mass number 1's also going to move mass number 2 because of this contact force between those two objects, or between those two blocks. So let's draw a free body diagram of mass number 1. So if I make that as mass number 1, there's my object. I know that I have the following forces acting on it. Weight force, normal force. I have this force that's being applied here. And I also have this contact force between M1 and M2. So M1 is going to push on M2, but M2 can push back a little bit too. So I have force of M2. Okay, now I want to know acceleration. They're wanting us to just find an equation or represent an equation for acceleration. I know that if this force is applied in the horizontal direction, these are my unbalanced forces here. So since it's moving in the x direction, I know the net force that will be accelerating would be in that x direction. So I can consider, since it's not accelerating, I don't have a change in motion in the y direction, my normal and my weight force would be equal to each other. But these two are where I would get my acceleration. So the net force in the x direction would be that applied force minus then the force of that second mass that would be pushing back a little bit on mass number 1. And I know since this isn't equal to 0 because we're accelerating it, we're moving these two blocks. I know that this can't equal 0, instead it's going to equal mass times acceleration in the x direction. right? Because force, the net force is just equal to mass times acceleration. And it's specifically in the x direction since that's the direction that it would be moving in. And then that equals the applied force minus the force that the second mass is pushing on M1. But let's think about mass, because we're thinking about this as the entire system. So because this is the mass of the entire system, I don't just think about M1, but I'm also going to have to take into account M2, because both of them would be accelerating. They're moving together, because M1 is pushing on M2, so they're moving kind of as a unit. So this isn't just M1, this is actually M1 and M2. So let's rewrite that even. So really we have M1 plus M2 for our mass, times our acceleration in the x direction, equals then that net force, that applied force minus the force that the second mass will push on the first mass. So if I want to get acceleration in the x direction by itself, then that's just going to be that net force in the x direction over the combination of the two masses. So there's my acceleration in the x direction. So we are done. Okay, let's go to the next one. On this example, it says a person weighs a fish of mass m on a spring scale attached to the ceiling of an elevator, because it's totally common to be in an elevator and weigh fish on a spring scale. Show that if the elevator, oh wait, Shannon, let's assume this is a monkey. So maybe not a fish, Shannon, it could be a monkey. Show that if the elevator accelerates either upward or downward, the spring scale gives a reading that is different from the weight of the fish. We want to first show that if the elevator goes upward, then I'm going to get a different reading on the scale than just the weight of the fish. Or if the elevator is accelerating downward, then it's going to show me a different weight than from the fish. So after we do that, we'll come up with some general equations, and then we're going to plug in some numbers to actually show that that's true. Okay, so let's draw a picture here for this. So we'll just show the upward one first. And remember, my drawing skills are very subpar, so no judgment here. Here's my elevator. And I have this, you know, I'm this person in this elevator because I'm weighing this fish. Let's just say it's on a little hook here. Okay, there's my fish attached to a spring scale in an elevator, and we can say that that is either accelerating upward, or we also need to think about it when it's accelerating in the opposite direction. So let's look at free body diagram. I want to think about a free body diagram in terms of my fish here. So we know this fish is attached to a spring scale. So we have some kind of we have tension or a spring force that's working here on the fish. And then we also know that the fish has weight. So I know weight force for the fish, and I also know it has this spring force here since it's attached to a spring scale. So we can just call that the spring force. We'll just call that Fs. So S just meaning for spring. I know that, let's say that the elevator is accelerating upward. So we'll pick the upward one first. So the elevator is moving upward, which means the fish is also accelerating then upward. So would these two be equal to each other if we have an acceleration in the upward direction? They would not. So if I think about my net force, which these would be in the y direction, I would say I have that spring force minus the weight force. But these aren't equal to 0. Instead, they're equal to mass times acceleration in the y direction, right? Because the net force is equal to mass times your acceleration. And then that's going to be equal to the spring force minus weight. Okay, but I want to simplify that down further because I know that weight is equal to mass times acceleration due to gravity. So really I could write m times ay equals that spring force minus weight, which would be m times g. Okay, but I want to get just the spring force. I want to know how would the spring force compare to weight if it's accelerating upward. So I would add that over here. So I would get Fs equals mass times acceleration in the y direction plus mass times gravity. Okay, which really means, let's just say that would be the same thing as mass times ay plus g. So there's my general equation for my spring force. So if the elevator is moving upward, then this acceleration is going to be positive, right? So if the acceleration is moving upward, the elevator is moving upward, this is going to be a positive quantity. So if I think about this, I have the mass times acceleration due to gravity, and we know that's just the weight of the fish. But if I also have to take into account the mass times the acceleration in which I'm moving, and that's a positive direction, then when the acceleration is positive, that scale is going to read greater than the weight of the fish. But let's say now that we're thinking about the acceleration in the opposite direction. Let's say that the acceleration is directed downward. That would make this acceleration a negative value. And if this were a negative value, then that means that the scale is going to read less than the weight of the fish. Now we know the actual weight of the fish isn't changing, but it's just because of this change in acceleration that we see something different on the scale. So let's plug in some numbers so then that way we can actually see that when acceleration is directed in a positive direction, the weight would be bigger than the weight of the fish, or the force would be bigger than the weight of the fish, and if the acceleration were in a downward direction, if it were a negative value, it would be less than. So we said specifically in this problem, let's say that the scale reads for a 40 Newton fish. So we know the weight of the fish is 40 Newtons, and the elevator, let's just say, has an acceleration of either a positive 2 meters per second squared or a negative 2 meters per second squared. So let's just do the upward, let's do the upward one first. Okay, so I know fish weighs 40 newtons. We just said to find that force of the scale, that is mass times acceleration in the y direction plus